You are watching the Geek Nerder podcast, and we are here to make you curious and inspire you with our deep tech talks on distributed systems, databases, stream processing, and general software engineering. Now sit back and enjoy the episode. Hello, and welcome to another episode. I have today Philippe from ParadeDB, and as you might have already guessed, we are going to talk about ParadeDB and how it works, and the internals and architecture, and some of the use cases that are really suitable for ParadeDB. So, welcome, Philippe, and I'm really excited to have you here. Let's start with a brief introduction about yourself, about your background, and what you're doing at ParadeDB.
Sure. Yeah. Thanks for having me. It's good to be here. A bit more about myself. I'm one of the founders of this Postgres startup called ParadeDB. We do search and analytics inside Postgres. Before that I worked on a different startup that was called Wist with many of the same team. We were building a browser, and I'm happy to share some of the stories of that. We did that for a few years. And before that I was a university student studying computer science at Harvard.
Awesome. So, I want to understand the historical context about ParadeDB. How did you come up with the idea, like using Postgres and like building search and analytics engine on top of it? So, what was the problem that you were trying to solve?
That's a good question. We started a company last summer in summer 2023, and at that time we were talking to a lot of engineers. In fact, we had worked doing some projects with a few companies where they were interoperating both Postgres as their primary database for storing, backend data, and another tool called Elasticsearch, which is pretty popular to do like very complex full text search or like search like experience within an application. And they needed to use both tools and send data from Postgres to Elastic. And the more data movement you do, the more complexity comes in. And Elastic has a lot of good benefits, but it also has its limitations and its sources of trouble. And so many of the people we talked to were kind of frustrated with that. And that got us interested in the space, and we thought we might be able to sort of upscale Postgres so you could remove the Elasticsearch part of that and have a much simpler infrastructure. And that's kind of how we got started.
Okay, interesting. And I guess I know the answer, like why Postgres, but I will still ask you why Postgres? Did you also try some other database?
No, we didn't. Postgres is wonderful. There's nothing better. So I think Postgres is by far the most loved database nowadays. Whenever people build a product, they first start with their database, and overwhelmingly nowadays people start with Postgres. It's very rare that people adopt other databases, and when they do, oftentimes it's people that already did, like big companies that did a long time ago, and those companies are moving to Postgres. There's many reasons why people love Postgres, which I'm happy to talk about. It's open source, community is very strong, it's obviously very reliable, and so on. But for all these reasons, we decided we were just going to do one thing and do it right, and we thought the best thing to do was Postgres.
Yeah, that does make sense. Postgres is such a vast ecosystem now, like so many users use it for different purpose. And I also love Postgres. Like I've been using Postgres since many years now. And that's why I said I probably know the answer, but I'll still ask you. Yeah, thanks for sharing that. You mentioned Elasticsearch, and I have personally, I've also used in my experience whenever, oh, we need a full text search, we need some kind of search functionality, let's spin up a new Elasticsearch cluster, ingest data, and then the data is searchable. That's the traditional way of doing search. And the problem I have faced typically is, of course, maintaining another Elasticsearch cluster itself is a big pain,
Mhm.
especially if there is a ton of data. And then maintenance work like upgrading Elasticsearch versions and making sure there's no regression and performance stays to the mark and all of that. So it's pretty challenging to have an Elasticsearch cluster. I'm sure there are other challenges, but I would love to take an example here. Let's say an e-commerce application where people can search for products and do some advanced search as well. And of course, they have transactional workload as well, right? Like creation of orders, things like that. So how would the architecture change when I remove the Elasticsearch part and try to embed, let's say, ParadeDB?
Yeah, that's a good question. It depends on the exact use case. So, in the example of an e commerce company, There's a few things. Like Elastic is pretty good if you have data that's not changing very frequently. So it works well, I would say, for some e-commerce, for example, because you can sort of index your catalog once, right? And then assuming it doesn't change very much, you don't have to worry about data movement so often. You can even do it manually in some cases, right? And that removes the number of moving parts. But typically, what people will do is they will start with Postgres, right? They'll have Postgres as their source of truth. It's very rare that people believe Elasticsearch is a source of truth. And so, if you don't believe it's your source of truth, then you need somewhere else with the same data that's stored that you trust, right? Because you don't want to lose any data, right? And so, and usually that place is Postgres. And so now most people already have within Postgres the data, and now you can create what we call them BM25 indexes, but search indexes on top of that data, and then just run SQL queries like you're used to. So the architecture would change. Typically, you remove one link of data movement, right? And afterwards, you route your queries. Instead of routing them to the Elastic search language or the Elastic cluster, you can keep routing them to Postgres. Another benefit you get from this is the world, as you said, has a big ecosystem around Postgres. There's so much that has been developed to make it really easy to run Postgres, to make sure multiple queries, running in parallel don't create performance decreases and so on. You can pull connections. You get to use all of these things and sort of abstract away a lot of the manual work you would need to do of setting up and maintaining Elastic.
Okay. But how does data reaches or get indexed for the search functionality? For example, let's say I have a catalog, as you mentioned. There's
Hmm.
probably orders coming through. Customers are placing orders. There's search history and whatnot. And I want to provide, let's say, search functionality on all of this data. So
Hmm.
how does the data that is going to the primary Postgres database, which is my source of truth, gets indexed, and how does that happen with ParadeDB?
So the way it works is we create this Postgres extension that we call PG Search. When you use ParadeDB, there's two ways to use our product. You could use our full Postgres distribution, which comes with our extensions built in, or if you manage your own Postgres, you could just use the ParadeDB PG Search extension. Once you have that installed, which is a simple command, right? You can then create indices on top of any tables you want. So let's say you have your catalog, your products table within Postgres. You could say create a search index over the products table. You can choose which columns you want to index, for example. You can also add tokenization if your catalog needs to be offered in multiple languages, for example. That's something that's supported as well. And then afterwards, every single new row or change that happens to your table gets automatically reflected in the search index. So let's say a new product gets added to your catalog, or that gets written, or a new order gets passed in by a customer, then that gets automatically reindexed and added to the search index, but it lives within your database. So you don't need to move data anywhere, which makes it much faster, much more reliable, and so on. And then when you run queries against your database, you would do it in a very similar way to if you do like simple select queries, but we have a few extra keywords that allow you to specify that you want to search in the search index instead of in the regular table.
Okay, interesting. So let's take the first case where, let's say, I have a Postgres database and I use the extension. So it's like creating the index, which I typically do with my tables. I have
Yeah,
to, let's say, run this command. So I also create an index which is specifically for search index using this new extension.
yeah.
Now, when the product is added to the catalog, is it like, when does it happen that the index is created? So typically when an index is created, it adds to the write latency. So is it done asynchronously, or it's done right when the actual write is happening to the product catalog?
That's a good question. So it is done when the write is happening today. So it's ever so slightly slows down your transactions. We are coming up with the ability for people to do eventual consistency, where instead of having the search be reflected right away, the transaction will commit, but the index might still be, regenerating, reindexing that specific row, which is something that in that case it wouldn't slow down transactions at all. But it also means if someone ran a search query like immediately, right, like it might not be there. In the same ways that if you need to send data over to Elasticsearch, for example, right, actually that delay is even longer because you need to transit data over the wire. In practice, it's very, very fast, which is why today all of our customers are using the strong consistency where the transaction only gets committed in Postgres once the search index is also updated. But it depends on your use case. And so that's why we're coming up with the other option as well.
Having it as part of write is should be fine for many applications, because at least in my experience these systems are not write heavy as compared to the reads or the search queries that they are making. So if there's a trade-off, basically, like your writes will be a little bit slow, but then you get like strong consistent search, which is
Mhm.
typically seen as a problem. And I've also faced this problem, especially with Elasticsearch, that the latency is higher and the data is not there yet. So serving like live customer facing analytics is really critical. And sometimes consistency is what you need. So it's ultimately a trade off. And as you mentioned, there's this async creation of index is also coming up for customers, which are fine with the eventual consistency type of model. I think it should work for them. What is happening though? What kind of index is created when, so let's say, again, taking the example of a product catalog, and I want to, let's say, I don't know, search based on some of the tags that I've added for the product and do a full text type of search. What exactly is happening? What kind of index data structure is created?
So what we do is we create like a pretty standard. It's very similar to Lucene, which is what Elasticsearch is built on, right? So we're built on our search functionality is built on an extension on a library, excuse me, called Tantivy, which is essentially a Lucene inspired search library that's built in Rust. And what we do is similar to Lucene, we tokenize words with it, and then afterwards we score words using the BM25 scoring algorithm, which is what Elasticsearch uses as well. It's essentially the state of the art, search ranking algorithm, and we return to you the results in that way. But I do want to clarify when you get a new entry added, a new row added to your table, we don't recreate the entire search index, right? We just add, that specific row. So the workflow for users typically is they have some data in Postgres, they bring in ParadeDB or PG search extension, they index their data once as it is. That might take, a few minutes, a few seconds, a few hours, a few days if you have like truly enormous amounts of data. And then afterwards, everything kind of stays up to date pretty rapidly.
Interesting. I'm I'm always curious to understand the index creation. Like whenever I do it on, let's say, live production Postgres databases, there's always a chance that create index could take a ton of time, and then you have to be really careful that it doesn't impact your live traffic. And then there is this create index concurrently type of feature in Postgres where you can, the index creation takes longer, but it doesn't take a lock on the table and create the index. So is there similar functionality available for this kind of index as well?
Yes, the idea of ParadeDB is to be as Postgres idiomatic as possible, right? People love Postgres and they love Postgres for a reason. We're not here to try to change the way you should use Postgres. We're more here to say, like, in the same ways that you've been doing everything before, you also should have the ability to do those more powerful functionalities.
Interesting.
So in general, that's our philosophy. Anything that you can do in Postgres, you should be able to do with us as well.
Yeah, I think that's a great philosophy because, as you mentioned, like people use Postgres for a reason. And then if that reason is slowly moved, I think it might be a friction for people to start using ParadeDB. So I think that's a good thing to have. Um, that makes sense. And so the data exists like a separate index structure within the same database. And that's when you say that it is fast because there's no network involved. You just have to create and maintain a new index structure. And that happens when you're writing the data. I see on the website it says, I don't know how fast it is mentioned, like 94x or something. I checked the website a few days ago. What is the reason of the speed that is achieved here? Is it mainly the network cost?
So the 94x is slightly different. That's for our analytics work. So
Hmm.
ParadeDB has two main functionality. One is full text search, and one is analytical queries. And our analytical queries are, yeah, about 94, 95 times faster than regular Postgres. I'm happy to talk about that if you're curious. But for the search side, the benchmark that we have is it's about twice as fast as Elastic when it comes to query time on about 1 billion rows of data. That's what we've tested. And the index build time is about 5 times faster. A lot of it, frankly, comes from optimization within being built in Rust, being a more modern implementation of Lucene, and so on. We Those numbers don't include the data transfer time of a full system. They include just benchmarking the actual search performance. If you were to add the time that takes for sending data over, then it would be sizably different, really, because I believe on a billion rows we were searching in about 200 millisecond or something like that. If you need to add a second or two or several seconds to just send data over the wire, then that starts to add a much more latency to the system.
No, I think that makes sense. And so I think the index creation part is clear. And but this is only for the full text search. But I see that there is like similarity search and hybrid search also supported. So how does that work? And could you give like a use case probably related to e-commerce that suits this thing very nicely?
Sure. So similarity search, we use pgvector, which you might be familiar with. So pgvector is a pretty popular open source Postgres extension that adds vector search to Postgres. It has the ability to store vectors and to search them. We had done some work with pgvector ourselves to add support for sparse vectors, which I'm happy to talk about. But now everything's been integrated into upstream pgvector, which the community benefits from. So that's what ParadeDB uses. We don't make any specific innovation there. The PG Vector is phenomenal, and there's so many brilliant people working on it. We're fortunate to be one of the benefiters from it. And then the hybrid search, what we do is we combine our work with full text search and PG search and the work of PG Vector to give you a few nice functions that allow you to combine the ranking and the scoring systems of the two. So in the case of e-commerce, for example, right, you could do a search by keyword where, let's say, you're searching for a MacBook, right? You can search that through the full text search system, try to find tokens that look similar to MacBook that hit the match with the word MacBook. Or you could say, like, give me a computer that looks similar to this or whatever, right? And do similarity search and say this is the like, I want all the shirts that are red shirts, right? And do similarity search based on the semantic meanings of the word red or of the word MacBook. And both of those are meaningful ways to try to retrieve information. But what's even more meaningful is the combination of the two. And pretty much every major enterprise, and especially every major e-commerce brands, for example, nowadays, they're all interested in hybrid search because you can give customers slightly better results, right? If you combine the best of both worlds. And so you might say, okay, you go on an online retailer, an online clothing brand, and you type red T-shirts, right? You want to say, okay, you want systems to be able to both find every T-shirt where the description includes the word red, for example, which would be more full text search like workload, and every T-shirt where the semantic meaning makes them similar to the concept of a red T-shirt, and that will return a greater number of results, or the results you get maybe fit both of those criteria, and you have more certainty in their accuracy, right? And that translates with more customer satisfaction and more sales and so on, and of course more revenues for those organizations.
Yeah. With this, let's also try to understand a bit more on the analytics side of the world. So I've done some episodes understanding how these analytics focused databases work, like Apache Pinot and Cows and so on.
Mm-hmm.
And then there's this column storage and things like that is fairly common. So how does analytics work in ParadeDB? What is happening when I, let's say, ingest? So as we mentioned, for full text, we create this inverted index and similar to what Lucene does. So for
Mm-hmm.
analytics, do you do something different?
Yes. Well, it's different than search, but it's very similar to ClickHouse and Pinot and those tools. So what we do is we modify two things within Postgres. We modify the storage system so it can store data in columnar format, like you mentioned, and we modify the way the query is being executed by Postgres so it can do vectorized processing. So basically, Postgres is a transactional database, right? That means it store data in a row format. And it also means that when it processes data, it processes one row at a time. And that makes Postgres very, very good to do what we call like point query retrieval, right? So you want to fetch information about your specific user account when you log into a specific platform, right? Postgres is phenomenal for this, but because people like it so much and it's become sort of the de facto standard language for communicating in the data infrastructure tool nowadays, people like Postgres to be able to do more and more things because every tool speaks Postgres. But if you're doing analytical data, you want data to be stored in column format because that's more efficient. And then when you want to retrieve that information, you want to retrieve it in batches instead of one at a time. Because typically analytical queries might say like, give me all the revenues from last month's sale, right? And so you want
Yeah.
to aggregate all the information. In order to do that, what we do is we integrate a few open source tools that excel at this within Postgres, but keep the Postgres shell. So from the outside, it just looks like Postgres, but internally we've modified a little bit the way the data is stored. So on disk, we store the data in Parquet files, which are a very standard compression file format for column-oriented analytical data. In memory, we use Apache Arrow, which is the in-memory version of the same concept. And then for executing queries, we use a query engine called Apache Data Fusion, which does this very fast processing of analytical data. So when you use the analytics side of ParadeDB, you can create tables as regular, but you add the using Parquet keyword to your table creation statements. And that informs ParadeDB that this specific data should not be stored in the standard Postgres format, but it should be stored in our analytics optimized format. And then whenever you execute queries against those tables, you don't need to do anything different. You just run your standard Postgres queries, but it's going to know automatically to do that batch processing, that columnar storage for it. And that makes it significantly faster than Postgres, roughly the same performance level as something like ClickHouse.
Yeah, that's very interesting. Interestingly, I've also done the an episode a couple of weeks ago about the FTAP architecture that you mentioned, data fusion and Parquet and Arrow, and it's very interesting. I want to know, so for search, as you mentioned, like there are two ways to use it. Like one can use the extension or the full distribution of ParadeDB. How does things work when it comes to analytics though? Is it because since you're changing the storage and changing a few things internally as well, so is it again just an extension or something else?
It is same way. You can run it within our own distribution, or you can just install the extension. And just to be clear, we don't modify any of your existing Postgres, right? We just essentially
Yeah.
add on a new extension that gives you the ability to store data in a different format. So if you have an existing Postgres with a lot of data stored in a bunch of tables and so on, nothing of that will be changed. But once you install the extension, you could say, hey, I want to start creating tables that are column. And then you can move some data over, for example, if you want, or you can just start writing data directly to those analytics optimized tables.
Interesting. And again, this is all happening within the same transaction. So when a product is added to a, let's say, a catalog, which is my regular table, like products table, and then I also want to do analytics on top of it. So is the ingest happening within the same transaction, or is it again happening asynchronously?
In this case, in the case of analytics, we're not an index, but we're a new table storage method. And so you need to write the data within that specific table if you wanted to benefit from those. So if you have a catalog table, right, that is a regular Postgres table, then and you write to that, it's completely independent of what you do on a different analytics optimized table.
Okay.
Typically what we see is our customers, they like this sort of HTAP workload where they get to do the best of both worlds. So data that needs to change very frequently, for example, oftentimes is good to keep in regular Postgres tables, and data that maybe not doesn't change as frequently, but when you so you might need to write a lot to it, but you might not need to update it heavily, for example. You want to write to an analytics table and be able to do the best of both worlds. You can even do queries in ParadeDB that allow you to do joins over both regular Postgres tables and analytics tables, but they're independent. So
Okay.
there's no really a concept of like weak or strong consistency in this case. If you write transactions to the analytics table, there's just your full transaction there.
Okay, interesting. So this changes the application logic a bit, where when I'm writing to the Postgres database, I also have to write to the analytics database and make sure if I need analytics on that particular entity or collection, I have to do that. Is that the case?
Yes, you would. Well, there's a few workflows. It's common for people to write the data twice. You can write it to both your regular row tables or to your column tables. It's even more common, I would say, for people to write it to only one of them. So typically, whatever data might need to be done analytics on, you'll just write directly to the column table, and you don't need to keep it in the row table. Afterwards, after all, it's Postgres. It's your source of truth, right? In the same way, you can think of it as just two tables within your Postgres cluster. Or something else you can do if you want is you can, when ParadeDB, we ship with another extension called PG Cron, which allows you to run cron jobs. You can do that, use that, for example, to migrate tables. So we have some customer use cases where, for example, you want the data to be written to a row table and every 5 minutes be converted into an analytics table. The benefit you get in this type of workflow is you can say, okay, for 5 minutes, this data might change very frequently. And then by the time you are pretty confident that it's sort of become immutable, then you convert it to analytics and you can do analytics on it. And you can do a trade-off, right? Everything's always a trade-off between data freshness, right, and throughput, which is something that you get to do. It's more, I would say this is kind of a rare case, but it's a case that we've seen as well.
Okay, that's interesting. So basically, I as a user, it's not exactly transparent to me, to the application, so to say, because I have to keep track and update the analytics table as well. But as you mentioned, there is also a cron extension which can take care of doing it every 5 minutes or on a period basis. And that works typically for cases when after this time, it's not going to be updated frequently, and it's good to run analytics on that.
Yeah, but I would say like maybe this is not the best example in that it's more of a niche situation. In most cases, it is quite transparent, right? Just like you might be using Postgres and ClickHouse together, for example, right, for different parts of your application. Now you get to just use Postgres for both parts of your application. You just specify which Postgres table. So you might have a live dashboard, for example, powered by analytics data. Instead of running queries against ClickHouse, you would run queries against your Postgres, but you would specify some table, right? And let's say your login flow might be using, Postgres, like the user settings flow, for example, might be using your regular Postgres. So we think it makes it more transparent, actually, and so it should be less complexity, not more.
That makes sense. I mean, essentially, it's less complex as compared to managing a different infrastructure just
Exactly.
for doing the same thing. And I always have this question when it comes to the state management. So let's say in the traditional way of doing things, if I have to ingest data into, let's say, ClickHouse or Elasticsearch, there's some kind of, I have my transactional database, of course, and then there's some infrastructure in between that is connecting the two pieces, like something like Kafka, which is there's CDC happening, and then the data is ingested into Elasticsearch.
Yeah.
Here, I have to update like both the tables, for example, right? So how does state management happen? So I'm talking about failure scenarios here. So if one call fails, for example, if I fail to write to the analytics database, how do I try to roll back? Because it's not exactly a transaction at the database level, right? Or can I wrap it in within the transaction?
It is. So
Okay.
again, we're trying to be purely idiomatic to Postgres. So
Yeah.
your analytics tables, they to the end user, to the developer, the experience should be no different than a regular Postgres table.
Okay.
So what this means is you have rollbacks, you have point in time recovery, so on and so forth. If you write a transaction to the analytics table and it fails, it should get rolled back or shouldn't get committed, right? Just like if you do that to a row or call a heap table, right? As for Kafka, there are many users that have been requesting that we add support for ingesting into ParadeDB via Kafka. That's not something that we do today, but that's certainly a very common way to ingest, especially analytics data, and that's something that will be coming at some point in the future.
Okay. Okay. Interesting. That's an interesting use case. So it's basically the architecture would then still remain like having an Elasticsearch, but still built on a Postgres, like Postgres, like Search built on a Postgres. But the overall infrastructure is going to be the same if you have Kafka in between and then the data is going into ParadeDB, right?
Well, you can set it in either way. You could have ParadeDB as a separate system that ingests data from Kafka, for example, or from you can get like logical replication from your primary Postgres. But typically, what we see is customers installing us directly within their Postgres, and then you can still ingest data, via Kafka in that world once we have the connection. Or eventually you'll be able to query data from S3 or just whatever data gets directly written to your Postgres. It's up to you. It's up to you what you prefer. Most of our customers typically they do as minimal data transfer as possible. So it removes the ClickHouse or the Elasticsearch part of it.
Cool. Typically, what I've seen in my experience is that, as I mentioned earlier, that these systems are not write heavy as compared to the reads and the search queries or analytics queries that happen. How do I scale my reads, for example, or search queries? So, for example, if I'm talking about Elasticsearch, I can have more number of nodes and machines that are serving my search queries, and that way I can scale it horizontally. Assuming, let's say, I'm using a Postgres database and I'm using this extension to create, let's say, search indexes and also the analytics tables. How does the read scalability works?
Yeah, that's a good question. I mean, analytics can be pretty write heavy, right? Especially the depend-only workloads. Search, as you say, is typically not as write heavy. Well, first of all, Postgres scales vertically very well. There are several users and customers that have come to us and were like, we need distributed, ParadeDB in so many ways. And it turns out if you take a server that's twice as big, your problems are fine, right? And it's much cheaper and much simpler to run on a single large machine than to run on a distributed machine. So there's a lot you can do there already to begin with. You can have multiple concurrent connections, for example. You can get machines with, more threads and machines with more network bandwidth as well if you need and more RAM. So that gets you a surprisingly long way. And not just with ParadeDB, to be honest. Like, you'd be surprised the number of production grade systems out there that are perfectly fine running on single node Postgres, typically with high availability and failover, right? Because you do want to ensure resiliency.
Yeah.
That being said, there are cases where this is not sufficient, of course, and you want to do things in a distributed fashion. We have customers today that are in that scenario, and typically ParadeDB is increasingly moving to have more of a distributed architecture as a potential support, only for enterprises for now, simply because, not that we're trying to keep things away from the developer community. It's only been enterprises that have needed that, to be honest. But that's more of I would say that's a smaller initiative, really. And then at that point, you'll be able to do everything you mentioned, right? There's multiple ways to do distributed Postgres today. There's a lot of phenomenal companies that have done it in the past and are still working and doing it today. And our plan is to be compatible with them so that you can easily keep your existing distributed Postgres and have ParadeDB integrate pretty seamlessly with it.
Yeah, definitely. I've seen, as you mentioned, like Postgres scales vertically very nicely, and
Very
people
nicely, yeah.
typically want to scale up before they try to scale out, because as soon as you have a distributed setup, it's really complicated.
Yeah.
But having one machine that works is definitely the most like simplest architecture you can have. So I definitely prefer that. But as you mentioned, there are some use cases where one machine might not be sufficient, and they want it. It could also be because of some compliance reason where they want higher availability than in certain numbers. So probably they're setting up more replication and read replicas. I think that should work fine. Um,
Yeah, so ParadeDB, so we you can do physical replication, for example, with our own Postgres distribution. There are a few things that need to come from our side to offer true high availability with every single component of ParadeDB. But those are like very high priority on our roadmap, of course, because even if you do single instance Postgres, you should have high availability, like no
yeah,
matter what, right? Unfortunately, there are some companies that advertise high availability as distributed Postgres. I think they do this because they're not distributed and they think it helps with their marketing. But there's actually a difference, right? There's a difference between single Postgres with no high availability, single Postgres with high availability, and actually distributed Postgres distros. And no matter what, I think you should have high availability
yeah.
because applications should be up, of course, right? So there's a bit of a difference between the two. We're focusing on doing that for most people, and in some rare cases, we do distributed.
Interesting. Let's assume I have just one machine. I have my search index created, I have analytics tables created, I have my transactional workload. I would love to isolate the workloads though, because I don't want my search queries to be impacting my transactional workload, like creation of orders, for example. So how do I create that kind of isolation? Is it at the application level, or also there is some support at the database level?
It depends. It depends what you want to do. If you have a single Postgres, if it's single on Postgres, you can't do that today. Um, so we like your Postgres would run every queries, right? If you're doing high availability setups or you're doing distributed Postgres, you can set specific shards to be responsible for specific tasks, right? When you're distributing the connections. And so then you start to have the ability to do that, which is something that we see often. Like customers, even customers that are not customers of ParadeDB will have, let's say, 10 read replicas, right? And specific replicas will be dedicated to like lightweight analytics workload. Because people, even before we came along, people did analytics in Postgres. Just simply because it didn't work very well, they could only do it at small scale. But they would still do it, right? And they would do it by dedicating a specific shard, for example, to that use case. A lot of people use Citus famously for things like that, right? And I know it happens as well on AWS Aurora as well. So that's another way in which you can do it. But of course, if you have like a single instance, then everything goes to that instance, right? Which it has some limitations, of course. You don't want your transaction to be slowed down by search queries, but for smaller companies at least, it's a good way to get started. I would
Yeah.
say before you start to do things at scale, and afterwards with high availability, you can get a good part of the isolation there. And if you really need, then you can also run multiple ParadeDB or other instances and dedicate specific workloads to each.
Yeah, that makes sense. I think the thing that you mentioned, it's easier to get started and it's fast, and it's easier to validate your idea before you
Yeah,
even start thinking about these problems where you need isolation. And then once you reach that, it's a good problem to have. Like you have more workload, more customers potentially, and then you can isolate them physically, and that's a
exactly.
good way. And it's a very standard way I've seen, at least in my experience.
The last thing I was going to say is the other benefit you get, and the reason we designed ParadeDB this way, is not so much that we're trying to tailor to smaller companies, but rather we're trying to make the transition very seamless, right?
Yeah.
So for there's a lot of systems out there where you need to either like do it fully at the enterprise scale from the get-go, right? Like run something that's distributed from day one and has this complexity, or you start with a non-distributed system and then it becomes very difficult and you need to do this very complex migration by the time you've reached scale and you're trying to scale it out, right? The good thing with Postgres is that transition can be pretty smooth actually because ParadeDB is integrated with as many of those tools as possible, and then there's many options to take a regular Postgres and distribute it. And so the idea is you can make the trade-offs that make sense to you today based on your situation without knowing that you'll be stuck in it in the future.
Okay. Yeah, that is a good point. One thing I miss as a Postgres user is the ability to let's say set up some kind of TTLs on my rows, and then the
Yeah.
cleanups become harder. Is there a TTL support that you're, let's say, you already have or planning to support, where I can say that until this point, for example, an e-commerce website, and I allow my users to search only the like last 6 months history of their, I don't know, their search history or their orders or things like that. And before that, like older data can be removed. So is it a possibility with ParadeDB at this point?
you so you could do certain things with triggers or PG cron and so on, but for the most part we don't have direct support for TTLs today. I have talked to enterprise customers who have their own PG TTL like extensions or functionalities that they add within their databases. It's possible to do things like that with procedural languages and custom extensions and so on. And so who knows? This is something that maybe we do someday. I'm taking note of your request. It's something that I've heard before and maybe something we do at some
Yeah,
point, like more formally. Yeah.
interesting. Yeah, at the application level, there is definitely ways you can shard your tables based on the timestamp and then just drop the table with older timestamp and all that. But again, if it's done seamlessly, at least for these use cases, I think it will be really beneficial. Another point that I typically face problems with, not problem as in it's a pain to upgrade your database, right, to newer versions. And not only the database versions, but also keep migrating to a new schema and adding columns, adding indexes, and things like that. So people typically end up using flyway migrations, for example. So how does it work if I'm using ParadeDB? Is it also supported with these kind of migration tools?
That's a good question for the specific migration tools. I don't know top of mind. I would need to check. I know people do upgrade our databases. I mean, you can upgrade the extensions pretty seamlessly, I would say. The core difference is we ship everything as a Postgres extension. So there's a lot of challenges that come with migrating databases that also come from the fact that the actual database version itself is being migrated,
Yeah.
right? All of this is not something that we specifically dabble with. So all these tools that help you upgrade your Postgres major version and things like that, like they work with ParadeDB, right? It's pretty independent. As for upgrading our extensions, well, we take great care to do backwards compatibility with our work now. It wasn't the case in the early days as we were, iterating very quickly, but now it pretty much is. And so typically it's as simple as running, the extension upgrade command, which is a single line command after installing the new version. Whether there's anything specific we need to do to make our extensions like supported in upgrading through these scripts, I am not familiar top of mind, so I would need to take a look.
Yeah. Okay. And these migrations are definitely, let's say, sometimes painful depending on
Mm.
how busy is your database. Having one system just upgrade both the type of workloads, like my search and my transactional workloads, would be definitely beneficial. What are the key differences between using an extension versus using a full distribution of ParadeDB? Is there like a feature difference, or is there just like operational differences?
Good question. There's not really any feature differences today. There's a few things. One is when you so as I said, there's kind of three ways to use ParadeDB. You could run our Docker image, which is our own distribution, or you could also run our Helm chart, which is essentially the same but for Kubernetes, or you could install our extension specifically directly using we prepackage them as .debs for Debian distributions of Linux, or you can even compile them yourselves if you want on like RHEL and on macOS and things like that. When you use our prepackaged distributions, you get a few things. One is you get both extensions already packaged. The feature difference would be you have, for example, the ability to do search indices over analytics tables if you use both of our extensions. If you only install one of them, obviously you won't get that. But if you do install both of them yourself in your own Postgres distro, you will. So we don't gatekeep any features like that. Anything that runs in our distributions, you can use on your own. And we ship a few other, nice to have extensions and configurations to improve the experience. We'll ship with PG Cron, for example. We ship with Postgres, which people often use together. We ship with PG Vector, right? Things like that. So you can think of it as sort of a batteries included version of it, but it doesn't have anything that it's impossible to do by just using the extension directly on your own.
Okay, interesting. So let's say I have my ParadeDB set up and my data is there, index is created, analytics tables are being populated. How do I know that everything is working as expected? And I need some observability on top of my tables and my search queries. What do I get from ParadeDB when it comes to the metrics that it publishes? And what is the recommendation? What should be monitored?
Yeah, good question. So you can monitor your, again, Postgres database the same way you would monitor ParaDB, the same way you monitor your Postgres database, right? So I mean, you can expect the plan, for example, right, to see where the queries are being, how the planner is making the queries and routing them, make sure the index is being used. You can check the queries per second. You can check the index size as well, which people often do. You can check the logs, things like that. Everything should integrate with all the tools that you use to manage Postgres today. Those are the main ways that we recommend. You can also query indexing time or indexing progress as well. For example, if you have a particularly large amounts of data, it might take time to index and you can query it to see how things are progressing. This is kind of the standard ways. Again, this is one of the areas we're trying to be as conformant to Postgres as possible, right? We take great care so that hopefully you've never used ParadeDB, but if you've used Postgres, you already know how ParadeDB works.
Yeah.
That's the hope.
Yeah. That makes sense because that reduces the friction. That
Exactly.
it's all the same, and that it's very seamless when I want to migrate to ParadeDB.
Exactly.
Okay, I think you have talked a bit about what's in your roadmap, but let's understand what's coming up. What are the top features that you're working on and releasing soon?
There's a couple of things. So, two of the features that I mentioned, we haven't formally released. They're in the product. You can use them, but we haven't announced them. So, there will be two things that we talk about heavily very soon in a more public setting. Think of it as sort of like a public beta access of them, if you will, right? For the
Yeah.
people that so much that they were willing to find out about them themselves. We call them HTAP joins. So, the ability to join correlative tables and row tables. Another big one that we already have built and that's releasing soon is search over analytics tables. So PG search indices over analytics tables. That's coming, or that's already in the product, but that's unannounced. And so I guess you're getting a scoop, hearing about them here in a public setting first. And then a big feature that we have coming up that's not announced yet is the integration with data lakes and cloud object storage. So many people have, especially analytics data, historical analytics data stored in AWS S3, right, or Google Cloud Storage or those platforms, and they want to be able to run queries on them from their Postgres or even correlate them with that. So that's something that's coming up very soon. That will probably be our next big release. And afterwards, there's, as I said, there's still a couple of small things that we need to do to give you full high availability and replication and things like that. So that will probably be what comes next. But those, are planning to keep us busy for some time, and customers always come with new requests. So things change as we go.
Yeah. Good luck with all the amazing features that you're building and releasing soon. I really enjoyed talking to you about ParadeDB and learning more about it. I'm also looking forward to the new features that you guys release. Good luck with that, and thanks for joining me. It was really a pleasure talking to you.
Well, thanks for having me, and excited to get your feedback on the new features as they come out.
Awesome. Thank you.